This week's Fluid Lab is on buoyancy and Archimedes' principle. We might even get in a little bit about specific density. All right, back in the old times, Archimedes was the top scientist and practical engineer and mathematician in the kingdom. And he was tasked by the tyrant of evaluating a crown to make sure it was pure gold with a few jewels, and it wasn't just plated with gold with some baser metals. And he was trying to figure out how to do this because he had to do non-destructive testing. He couldn't just take a chisel and go through it because he'd ruin it. And he was getting worried because the emperor was getting mad and his life was about to be snuffed out. So he's thinking, he's chilling in the tub, he's lying down, and then he leans back deeper and immerses himself much deeper. And he notices two things. He felt lighter. He wasn't being pressed against the tub, and the water level rose. He had an epiphany. He jumped out butt naked, went screaming through the streets, saying Eureka, because he had found the solution to save his neck. What he figured out was this: how to figure out the crown. So he decided to take the crown and put it in a bucket of water. Now normally he would have just taken the crown, counterbalanced it with the gold, and then if he knew the volume of the crown, he could check out the density. But the problem was it was such an irregular shape that this math whiz couldn't do it. So then he immerses the crown in here and the water level rises. He takes the crown back, it falls. Then he goes out to the royal bank and he keeps adding gold and gold pieces until the water comes back up to the same. He dries the gold, puts the gold on one side of a double balance, puts the crown on the other, and he figures, give or take 10%. If it's cool, it's mostly gold. And that's the story. Some of this technique we're going to use here, only in the sense of weighing it under the water. Now, one thing he discovered was that he correlated the fact that he felt lighter with the displacement of the water. And he said, Archimedes' principle, that the upward buoyant force, appearing to be less weight, was equal to the weight of the displaced fluid. In this case, the water he pushed out. And we're going to verify that. Now, in terms of a little bit more physics, we can know the true story. If this is a fluid, and here's the level, and here's an object completely underneath it. Going to the colored pens, because I'm so prepared. All right. A guy named Pascal discovered that one of the natures of fluid molecules is they flow. They seem to transmit the pressure, the force per area, undiminished. And there's a variation in pressure with depth. At this depth, everywhere, it's pretty low. But you add this column of water, the weight of everything above it, when you get up here, it's pretty big. In the middle, it's about halfway. But the pressure pushing up on the bottom is a lot bigger than the pressure on the top. And that change in pressure times the area is the buoyant force. And so we want to prove that Archimedes was right. So here's how we're going to do it. In Mesa College, wait, slow down. Well, you're going to weigh this aluminum solid in the air by counterbalancing it, which I've already done. The date is there. So this would be roughly 240. This a 2, this a 5. There it is, give or take. Okay, and then we're going to weigh it completely submerged under the water. Sample data is on the board. Completely submerged, not touching the bottom. We don't want any normal force, not touching the side, no friction. And it's going to weigh less. The difference in what it weighs is the effect of the buoyant force. The sample I like to do in lecture, if I were doing a lecture, is if I get on a scale at my swimming pool and it's waterproof and I look down, it's 200 pounds. The water level rises, comes over my head, I'm completely submerged. I hold my breath, I look down. The scale has now been reduced to 25 pounds. That means the buoyant force must have been the difference between the 200 pounds versus the 25 pounds when completely submerged, or 175 pounds. That means if I had a way of collecting the water I filled out, maybe if I walked into the pool and I had an overflow, gutters, I would collect 175 pounds. Well, here we have a better technique. So here's what's going to happen. I already filled up this thing to the overflow position as a spout. The way I knew it was full is I overflowed it. So now in the minute it touches there, it's going to push out the water. This takes years of practice because it's tricky. So you've got to hold this thing here. And now I'm going to slowly have it hit the water. Normally I'd have a partner or two, but hey, I'm a professional. Corona won't kill me. It might get you though. I gotta go slowly so it doesn't overflow. No. Take it easy, almost there. All right. And now I'm gonna tie this thing off. Good luck. It's on the bottom, not a problem. And when I balance it, it won't be on the bottom, because when I balance it, it's going to come up like this. So while it's collecting the water, I can figure out the weight submerged. It won't be 200.4 newtons. It's going to be a lot less. This is too much at 2 newtons, so it's already got lighter. Your data is different, but let's just play around. This is 1.5 newtons. And we're getting close. And given 20 minutes of film time, I could balance it, but I've done this a couple of times. And it's approximately 1.524 newtons. You're getting different data, though. And there's a difference between being 2.40 newtons and 1.52 roughly newtons. That difference is the buoyant force. That buoyant force should equal to the weight of this water that was pushed out. I already weighed this empty. I can weigh it with water on the scale. And through the magic of arithmetic, I can subtract those two weights and find out the weight of the water. The weight of the water that was pushed out should be roughly equal, within a couple of percent, the difference what it weighs outside the water versus completely submerged. The data is on the board for different data, and we can take a look at it. In the air, it was 2.205. Submerged, it was this. You're going to have to subtract these two to find the difference. Here's the water, catch bucket empty with water. You have to subtract those two to get the weight of the water. The weight of displaced water will be roughly the buoyant force, the difference of what it weighs outside the fluid and completely submerged. And if Archimedes is right,